Hi everybody, in this video I'd like to show you the derivation for the differential equation used to solve a spring mass system. I have here a spring mass system. This is a horizontal spring mass system where the spring is attached to a barrier, and right now we will assume that the mass is here at the equilibrium position where it's not moving, and then we're going to give this an initial position and start to see the motion happen. The mass is going to oscillate back and forth around the equilibrium position. In this animation, I am assuming that there is no friction. We will allow for there to be friction later on in the video. And it's also worth noting that I borrowed this animation from a page on Desmos, the link to which you will find in the description below. Let's stop the mass right here and take a look at what's going on. The only force acting on the mass is that from the spring, and we will assume that the spring abides by Hooke's law. Hooke's law says that the force is equal to negative k times x, where x is the displacement, how far away the mass is from the equilibrium position, and k is a positive constant. The reason for the negative is that we again are looking at the force acting on the mass. When the mass is on the positive side of the equilibrium position, the force exerted by the spring is pointing in the negative direction. And when the mass is on the negative side of the equilibrium position, the force exerted by the spring is pointing in the positive direction. So the spring is exerting a force that is in the opposite direction of where the mass is in reference to the equilibrium position. Again, in this first example, we are going to assume that there is no friction acting on the mass. So we're going to let x of t be the position of the mass in reference to the equilibrium position. Newton's second law says that the sum of the forces acting on the mass needs to be the mass times the acceleration, and the acceleration is the second derivative of the position. So we will write Newton's second law as mass times the second derivative of x, and that needs to be equal to the sum of the forces acting on the mass. There is only one force acting on the mass, that from Hooke's law, so mx double prime is equal to negative kx. I can rewrite this and put this in the form of a homogeneous differential equation. Mx double prime plus kx is equal to 0. And we will say that the initial conditions are that x of 0 is equal to some initial position x sub 0, and x prime of 0 is equal to some initial velocity. And there you have it. That is the differential equation for the spring mass system, assuming that there is no friction. Next, let's assume that we have friction and that it is proportional to the velocity of the mass. Now, when the mass is moving in the positive direction, the friction will be pointing in the negative direction. And when the mass is moving in the negative direction, the friction will be pointing in the positive direction. So we get that friction is always going in the opposite direction of the mass. We can say then that the force due to friction is equal to negative c times the velocity, where c is a positive constant. Again, just as in the last example, we see that negative there because the force is in the opposite direction, in this case, of the velocity. Velocity is the derivative of the position, so we will say that the frictional force is negative c times x prime. Again, going back to Newton's second law, we get that m times x double prime is equal to the sum of the forces acting on the mass. We have the force due to the spring, negative kx, and the force due to friction, negative cx prime. I can rewrite that in the form of a homogeneous differential equation, mx double prime plus cx prime plus kx equal to 0. And just as in the last example, we have initial conditions of x of 0 is equal to some initial position, and x prime of 0 is equal to some initial velocity. Hey, thank you for taking the time to watch this video. I hope that you found it helpful, and I look forward to seeing you in the next video.